All right, this is softening. What is hardness? Hardness is the measurement of the soap or detergent consuming power of water. Two main components that are mostly attributed to hardness are calcium and magnesium ions. They are metals and usually bonded with other materials, carbonate and bicarbonate. Hardness is usually measured, expressed as milligrams of calcium carbonate equivalent per liter, also grains per gallon. 1 grain per gallon equals 17.1 milligrams per liter. Common hardness ranges, so I get a lot of different ones in different places I look. We're going off the Sacramento State. 0 to 60 milligrams per liter is soft water. 60 to 120 milligrams per liter is moderate or normal. 120 to 180 milligrams per liter is hardness. 180 milligrams per liter or greater is very hard. How do you measure hardness? Lab tests. So you can titrate with EDTA, which will turn from a red to a pure blue color, which is the endpoint. Results will be shown in grains per gallon total hardness. Alkalinity is measured as a result of titration as well in two distinct parts. You have the phenolphthalein alkalinity, which is P alkalinity. So it is present in a sample with a pink color when you add the drops. You also have total alkalinity. So when running the test, the phenol indicator is added if the water turns pink. Then you have phenolphthalein alkalinity, P alkalinity. You'll titrate till the pink color is gone and record the number. After you find that, you add another indicator which should turn green, and then you'll titrate, and that will give you the total alkalinity when it turns a red color. So hard water is undesirable because it causes the formation of soap curds, increases the use of soap by inhibiting the cleaning action of the soap. It deposits scale, and it can cause an objection of taste. So how is water softened? Chemical precipitation, lime softening, where you also have ion exchange. Chemical precipitation, also known as lime or soda softening. Hardness is not reduced to 0. The minimum hardness achievable is between 30 and 40 milligrams per liter. Is very expensive. Most plants will target 100 to 150 milligrams per liter. Low hardness finished water equals more lime sludge and higher treatment costs. But for 1 ton of lime used, it creates 2 to 3 tons of waste. Let's have ion exchange softening. Hardness can be reduced to 0. But very soft water can be corrosive. The exchange of sodium for calcium magnesium takes place on high resin charged with sodium chloride. Calcium and magnesium stay on the ion exchange, and the sodium ions will leave. The benefits of softening: it removes hardness, iron and manganese, enhanced corrosion control when water is properly stabilized, slight film scale in the pipe, not too excessive, it's not bad. Enhanced disinfection when using lime softening due to high pHs. It reduces some taste and odors, and it removes some natural radioactivity. Limitations of softening. Free chlorine is not as powerful in the hypochlorite ion form, which occurs at the higher pH levels. The cost versus benefits: for every 1 ton of lime used, 2 to 3 tons of waste is produced. You have to dispose of that waste. Trihalomethanes form at the higher pHs if using free chlorine. If water has color in it, the high pH can set the color in place, making it harder to remove later. So waters with high color, it's recommended to using the coagulation flocculation process to remove the color before softening. You have 2 types of hardness. You have temporary and permanent hardness. Temporary hardness is carbonate hardness. So you would have like calcium bicarbonate, magnesium bicarbonate. It's easier to remove and not as chemically intensive. Temporary hardness can be removed with lime only. Temporary hardness again is in the form of calcium and magnesium bonding with either bicarbonate or carbonate. Permanent hardness is non-carbonate hardness. So in the state of Florida, where I'm at, you have calcium sulfate, calcium chloride, magnesium sulfate. Permanent hardness removal requires both excess lime and soda ash. Non-carbonate hardness is from magnesium sulfate, magnesium chloride, calcium chloride, and calcium sulfate. Other parts of the country can have nitrates and silicates, which would need ion exchange versus softening. Total hardness equals calcium plus magnesium hardness. Alkalinity. Alkalinity is the capacity of water to neutralize acids. It's caused by the water's concentration of bicarbonate and carbonate and hydroxide. Silicate, borate, and phosphate also contribute to alkalinity. It's measured as milligrams per liter of calcium carbonate equivalent. Lab tests include portable test kit, lab spectrometer, Roman scroll green, or with a pH meter and sulfuric acid for titration. The water alkalinity is how much carbonate hardness is present. So calculating carbonate versus non-carbonate hardness. If total alkalinity is greater than total hardness, then all the hardness is carbonate hardness, temporary. If hardness number is higher than the alkalinity number, then the non-carbonate hardness is present, permanent hardness, along with carbonate hardness, temporary. By subtracting the total alkalinity from the total hardness, the amount of each type of hardness can be determined. Permanent hardness equals total hardness minus alkalinity. So here's an example. If you have a total alkalinity of 250 milligrams per liter of calcium carbonate and a total hardness of 100 milligrams per liter of calcium carbonate, the total alkalinity is greater than total hardness, therefore all hardness is carbonate hardness, temporary hardness. For another example, if you have a total alkalinity of 182 milligrams per liter and the total hardness is 233 milligrams per liter, the total alkalinity is less than the total hardness, therefore permanent hardness exists. To find out how much permanent hardness exists, you take the total hardness, 223 milligrams per liter, minus the total alkalinity of 182 milligrams per liter, which would give you 41 milligrams per liter of permanent hardness. So by understanding the amount of hardness and alkalinity of source water that is to be treated, we can determine how much lime and possibly soda ash that will be needed to treat water to a desired finished water hardness. By knowing how much carbonate, bicarbonate, and hydroxide chemicals are present, operators can properly dose the softening chemicals like lime. Alkalinity chart is used to determine how much of each type of chemical is present in milligrams per liter. Don't forget to look at the alkalinity relationship chart. Study that because we've got math questions, but it's audio notes. Can't really see it right now. All right, so pH. pH is the potential for hydrogen. It exists as two ion forms. The hydrogen ion, which is usually going to be H plus acid, or a hydroxide ion, OH negative, and if more of those are present, they're going to be more alkaline or caustic. pH of 7 equals water, so you have equal amounts of the hydrogen and hydrogen oxide ions. The pH scale goes from 0 to 114, 0 being acid, 14 being base or caustic. Most natural source water is 6.5 to 8.5 pH. The pH of water can be raised or decreased by adding chemicals. The relationship between pH and alkali constituents in water. So this is how lime softening works. You are adding lime to raise the pH to convert these different constituents so that they will precipitate out. So you have CO2, which exists naturally in water as a dissolved gas and can be present in water. CO2 affects the pH and alkalinity as it forms carbonic acid H2CO3 in water creates a demand on lime softening chemicals when present. So you're starting at a pH of 4.3. As you start raising the pH, CO2 will turn 100% into bicarbonate at a pH of 8.3. So 4.3, 8.3, as you raise the pH, CO2 is turning into bicarbonate, right? Also, you keep raising the pH, bicarbonate will turn 100% into carbonate at a pH of 10.2. Continue to raise the pH, carbonate will turn into hydroxide at a pH of 11.3. Is at the pH of 11.3, all bicarbonate have been converted to carbonate, then to hydroxide forms. The calcium carbonate has precipitated, and what you'll be left with is like magnesium hydroxide, which will now also precipitate. So treatment chemicals that will lower pH and alkalinity of water, acids, aluminum sulfate, coagulant, carbon dioxide, lime softening, gaseous chlorine, disinfection, ferric chloride, that's coagulation aid, hydrofluoric acid, which is for fluoridation, and adding sulfuric acid, which you add for pH control. Treatment chemicals that will raise the pH and alkalinity of water, making it bases. Calcium hypochlorite, which is the disinfectant. Sodium hypochlorite, bleach, disinfection. Sodium hydroxide, caustic soda, which is used in softening. Sodium carbonate, which is soda ash, which is also used in softening. And sodium aluminate, which is used in coagulation and flocculation. So the lime softening process, this all happens simultaneously. Step 1, add water to unslaked quicklime, CaCO. This produces hydrated lime, CaOH2, or slaked lime, and heat plus grit. Step 2 is to meet the carbon dioxide demand. It's by adding lime to the water. Converts carbon dioxide first, CO2. Does not need to be removed, but is consumed some of the lime. The pH is raising to 8.3. So CO2 plus CaOH2 becomes CaCO3, which precipitates and water. Step 3, convert CaHCO3 to CaCO3. So to get the calcium to supersaturation, we add more lime to convert the calcium bicarbonate to calcium carbonate. Your pH is raising to a 10.2. Step 4 is you want to convert the MgHCO3 to MgCO3, so enough lime is added to the water to allow hydroxide to become present. Magnesium bicarbonate, the MgHCO3, 2, converts to magnesium carbonate. pH is at 11.3. Step 5, you want to convert the MgCO3 to MgOH2. With enough lime added, magnesium carbonate becomes magnesium hydroxide and will settle out with the CaCO3. This will complete the carbonate hardness softening. So at 11.3, your temporary hardness, your carbonate hardness, has been converted. So to remove non-carbonate hardness, permanent hardness, the magnesium chloride, magnesium sulfate, calcium chloride, notice that none of those have carbonate in them. You're going to dose with excess lime, so about a 15% overdose. So magnesium hydroxide will settle with excess lime addition. The pH is now above an 11.3. Sodium carbonate, soda ash, is used to remove calcium sulfate. So sodium carbonate, soda ash, is used to remove calcium sulfate. Calcium sulfate and soda ash become calcium carbonate and sodium sulfate. Calcium carbonate can settle out. So recarbonation. If the pH is now lowered, the precipitation of calcium carbonate and magnesium is improved. along with allowing the excess lime to settle. Recarbonation is usually a two-step process. First, reduction of a pH to 10.4, which encourages the precipitation of CoCO3 and MgOH2, then reducing the pH to a 9.8 or less to encourage non-carbonate hardness to precipitate. Step 9 is the removal of all lime from the system. Waste sludge comes out the bottom of the clarifier. Periodic or automatic manual wasting occurs based on lime level or time. Wasted lime goes to a lagoon or disposal system. Caustic soda. Caustic soda can be used to remove hardness from water. When reacting with CO2 and carbonate hardness, caustic soda forms sodium carbonate, permanent hardness. Why use lime instead of caustic soda? Lime is much cheaper. Using 50% caustic soda has some advantages. It's more stable for storage, there's less sludge byproduct, and it is easier to store and handle than lime. Alright, some keynotes about softening. Excess lime / soda ash is primarily used if non-carbonate hardness is high. So excess lime or soda ash is used for non-carbonate or permanent hardness if it's high. Lime softening is for carbonate hardness, temporary hardness. Split treatment can be used in waters high in magnesium. The pH of water after softening can be very high. For every 1 ton of lime used, 2 to 3 tons of waste sludge can be produced. Lime softening's high pH tends to set the color. Color should be removed by coagulation, pH of 6 and 7. Operators should know what the source water hardness is and what the finished water hardness goal is. The chemical dosage is based on the desired finished water hardness goal. There was math, but these are audio notes, so I'm not doing math right. Reducing pH too fast by adding too much CO2 can cause some hardness to become soluble again, and make bicarbonate hardness again, like you didn't just treat for the hardness at all. Lime soda softening is chemically intensive. Operators need to know about the relationship between pH and hardness / alkalinity when it changes forms from one to another. Again, as we're raising the pH, we're changing the forms of the alkalinity. That goes back to that chart, the pH and alkalinity constituents in water chart, converting from carbon dioxide all the way to bicarbonate, bicarbonate to carbonate, from carbonate to hydroxide as you raise the pH. Split treatment for water that's high in magnesium. About 80% of the source water is treated with an excess lime dose to raise the pH over 11.3. The rest, the 20%, is bypassed to the next tank to lower the pH of excess lime treated portion. If permanent hardness is still present, the second stage adds soda ash to treat non-carbonate hardness. Split treatment can eliminate or reduce need for recarbonation and purchasing CO2. Split treatment can reduce overall costs. Again, these are just some quick notes to listen to while I drive around the car. And that was lime softening.